Hello friends, welcome back in this video lecture of Nuclear Magnetic Resonance Spectroscopy part 3. So in the previous part we have already seen what is chemical shift and what information we can gather from recording and proton NMR. We have also seen the various solvents used in NMR spectroscopy and why TMS is used as an internal standard. Now in this part we will be discussing factors affecting the chemical shift. So what are the factors affecting chemical shift? The first and very important factor is the electronegativity. Now this electronegativity factor is also referred as shielding and deshielding, because the electronegativity causes the protons to shift in a shielded zone or to a deshielded zone. In theory of NMR, we have already seen the nucleus of the proton has the spin moment and it has a charge. So it is spinning in a gyroscopic motion and it is generating its own induced magnetic field. The moment we expose these spinning nucleus into an applied magnetic field B0, the gyroscopic motion of the nucleus of the proton will change to a precessional motion. And what we do in NMR spectroscopy, we match this precessional frequency under the influence of B0 with that of the radio frequency beam, and we bring them into a resonance. So that's why we consider it as a nuclear magnetic resonance spectroscopy. So what usually happens, the nucleus of the proton is also surrounded by the electrons, and we know electrons are also charged particles which carries a negative charge on it, and they also have the spin moment. So these electrons which are surrounded or covering this particular nucleus surface, they are the charged particles, negatively charged, and because of the electron cloud and because of the spin moment, the electrons will also generate its own magnetic field, and this own magnetic field generated by the electrons will either help this particular proton by aligning themselves to the opposed direction to the B0, okay, or it can be parallel to the B0. So what happens if the electron cloud surrounded by this particular nucleus of the proton is very dense? Then it will protect this particular nucleus in a very strong way from that of the influence of external magnetic field. So if the proton are surrounded by the electron cloud, now the net magnetic field which is experienced by this nucleus of the proton is no longer effective by this B0, but it will be subtracted by this sigma. So we can have the B effective is equal to B0 into 1 minus sigma. Now this sigma is nothing but the magnetic field which is generated by the electron cloud surrounded by this particular nucleus. So this is usually very negligible. It is in the power of 10 raised to minus 6, and that is how there is a small shift in the actual position of this particular set of proton. Okay, so that's why we usually record the delta values in a ppm. Okay, so what happens if the electron cloud surrounded by this nucleus is highly dense, and this electron cloud which has generated its own magnetic field which is diamagnetic or which is opposing to this applied magnetic field B0, so they will help this particular nucleus of the proton, they will protect or they will shield this nucleus of the proton with the influence of this external magnetic field. So that's why they are called as a shielded protons. Okay, and because of that the B0 is precessing now this nuclei at a lower frequency. So the precessional frequency of such nuclei which are surrounded by a very dense electron cloud, it will be lower, and because of that we require lower radio frequency to bring these precessional frequency of nuclei into a resonance, and hence the shielded protons are appearing at lower delta value. On the other hand, if the nucleus of the proton is less dense the electron cloud surrounded by this nucleus of the proton is lesser or not denser, then what will happen? It will not be protecting this particular nucleus from the applied magnetic field B0, and that's why the nucleus of the proton will be precessing at higher frequency. So rather we can consider it as they are deshielded protons, okay, because the lower density of electron cloud, and hence because of less shielded or deshielded, the B0 is precessing them at very high frequency, and that's why we require the higher radio frequency source to bring them into a resonance, which results the higher delta value. Okay, so this particular figure also indicates the effect of shielding and deshielding. So here we can see the nucleus of the proton. So these horizontal lines are indicating the spin movement of this particular nucleus, and because of the spin and because of the charge, it is generating its induced magnetic field, and the electron cloud surrounded by this will also have the induced magnetic field. Now this induced magnetic field is usually moving in this particular direction on this half, and on the other half it is moving in this particular fashion. Okay, so we can see the direction of the induced magnetic field on this particular zone is aligned with the B0, that is applied magnetic field. Okay, so they are parallel to each other. So if they are parallel to each other, then they are deshielded. Okay, so in that case, if something is coming in this particular region, it is not protecting themselves from this B0 and they will be deshielded, or they are paramagnetic, parallel to the applied magnetic field. But if something is coming exactly at the center, it is diamagnetically. You can see the arrows are pointing towards the B0 or opposite to B0, so they are called as a shielded zone. Okay, so shielded zone, that means they are opposing to the B0, and because of that they will be precessing at lower frequency. So this electronegativity effect can be understood with some examples. So I have represented here table compound CH3X. So we will be mainly focusing about this CH3 protons, and X could be any electronegative or electropositive atom here. Now you can see in case of CH3F, so you know fluorine is highly electronegative in a periodic table. So the electronegativity of fluorine is 4.0. So because of that, the fluorine, which is electronegative, will attract the electron from this hydrogen atoms, 3 hydrogen atoms, through the carbon. Okay, so because fluorine is attracting or withdrawing the electron cloud from the 3 hydrogen through the carbon, the electron density surrounded by these CH3 protons will be minimized, and because of that the net magnetic field which is experienced by the nucleus of this CH3 proton will be in a deshielded zone, and that's why you can see the chemical shift of this CH3 protons which are attached to a fluorine is appearing at 4.26. If you move from fluorine to a lesser electronegative like OH, or chlorine or bromine, you can see the electronegativity decreases, then the chemical shift is also decreases. So there is a direct proportion between the electronegativity of the atom and the chemical shift value. You can see here the iodine. So iodine is lesser electronegative than bromine, than chlorine, or OH or fluorine. So you can see here these are appearing at 2.16. Then we can have a tetramethylsilane, where silane is rather electropositive. So this silane is rather releasing its electron towards the carbon, and from carbon it is going towards the hydrogen. So the hydrogen in case of TMS is experiencing more electron cloud surrounded by itself, and because of that the nucleus of these methyl proton attached to the silane are having a very good electron cloud, and because of that they all together will protect the nucleus of this proton and they appear near to 0. Okay, so we use this tetramethylsilane as a reference standard. So in fact, in practical, the tetramethylsilane protons have some delta value. Okay, it has some chemical shift because of the electropositive silane, but we consider it as our convenience, we consider it as a 0, and with respect to 0 we plot other values. Okay, so but remember, the TMS also has some chemical shift, but for our convenience we are considering it as a 0. Okay, so this effect is also there when we have substitutions. You can take an example of CHCl3, that is a chloroform. Now here, in case of this, we are talking about only this CH protons. Now this CH is connected to a 3 chlorine atoms. So here the electronegativity effect is very pronounced because of the 3 chlorine atom. It is withdrawing the electron cloud of this hydrogen atom through the carbon very effectively, and that's why this proton is experiencing a net deshielding effect, and that's why they are appearing at a very higher delta value. It is close to 7.27. As you substitute one of the chlorine with the hydrogen. Okay, so you can see here, in case of dichloromethane CH2Cl2, the effect is reduced. Okay, now if I am making it CH3Cl, again the effect is reduced. Okay, so it is appearing at 3.05. Then you can have a bromine, and if I am introducing here, you can see in case of CH2Br it was at 3.30, but if I make one more CH2 in between them, so this bromine, which is again a electronegative, will withdraw the electron through this carbon of this particular hydrogen. Okay, in a lesser way as compared to this what we observe here. So that's why these protons are highly deshielded compared to this CH2 protons. So that's why you can see it is appearing at 3.30 where it is appearing at 1.69. The effect is again minimized as you introduce the atoms in between. So here there are two CH2s, so still the bromine can withdraw the electron from this CH2 through these two carbon atoms, but this is not that much effective as what we are observing in this 1.69 and 3.30. So as the substitution increases, you can see the chemical shift value will decrease, or the effect of electronegativity will be minimized. So in one slide we can summarize this. Higher the electronegativity, then there will be more withdrawal of electron from the proton, and that will reduce the electron density surrounded by that particular nucleus of the proton, which results in deshielding. And because of the deshielding, the chemical shift value will be in a downfield region. Okay, towards it will be towards the 12. Now the next factor, that is a van der Waals deshielding, or it is also called as a steric hindrance. So we know in a rigid molecule which have protons at a sterically hindered position, and in consequence the electron cloud of the hindering group will tend to repel each other because of the electrostatic repulsion and the electron cloud surrounding the proton. Okay, so this usually will result in a deshielding and appear at a higher delta value. So though this effect is usually very small, it is usually less than 1 ppm, but it should be taken into consideration when we are analyzing such type of molecules. So for example, we can see this particular methyl proton, this is separated by one bond. Okay, then these methylene protons are deshielded by 2 bonds, and this methine protons are deshielded by 3 bonds. So you can see here this is more sterically hindered. Okay, so that's why these protons will be more deshielded, okay, compared to the other one. So as the steric hindrance increase, the particular nucleus is at isolated place, then the effect will be towards the deshielding zone. Okay, the delta value will be higher, and it will be usually the effect is plus 1 ppm. Then the third effect is a anisotropic effect. So keep in mind, anisotropy means it is isotropy is a similar, anisotropy is it is not similar. Okay, so the chemical shift of aldehydic, alkene and aromatic protons, they usually appear at a higher delta value than can be accounted for electronegativity effect alone. So whereas alkyne protons appear at relatively lower delta value. So why this is happening? In some cases, some type of protons, the delta value is higher than what we predicted considering only the electronegativity effect alone, and in some cases it is different. Okay, so that can be accounted by this anisotropic effect. Here we have represented some of the examples of different sets of molecule. So when we have the aldehydic protons, here you can see in this case the approximate delta value is from 9.5 to 10. If you have alkene protons, carbon-carbon double bond, and the proton is here, so these types of protons will usually appear in between 4 to 8. Whereas if you have aromatic protons in a ring structure, it will be appearing in between 6 to 9. And when you have alkyne protons, okay, acetylene type of protons where it has a carbon-carbon triple bond, it is appearing in between 1.5 to 3.5. So why it does so, we can get into that. So you can see here this particular figure which is representing anisotropic shielding and deshielding around an alkene proton in this particular figure A. Okay, so we can see when we take alkene molecule under the influence of external magnetic field B0, the molecules will arrange in this particular fashion, and the induced magnetic field which is generated by the nucleus of the proton is in this particular way. So this cone which we have represented with this dotted line, okay, where this induced magnetic field is generated. Okay, and here we have the axis at the center where our B0 applied magnetic field is acting. Okay, so you can see the protons are in a de-shielded zone. Okay, because at the center we have seen at the center it is a diamagnetic, and on the periphery it is a paramagnetic. So anything which is coming in a paramagnetic zone, it will be a de-shielded. Anything which is coming in a diamagnetic zone or at the center which is opposing to the applied magnetic field, that will be a shielded one. Similarly, you can see a carbonyl. Okay, so this is usually having 43-degree angle. Here it is 36. So that's why this because of the 43 wider kind of angle, you can see the cones, and this is in case of carbonyl type of C double bond O compound, the protons are very close to the periphery. Okay, so they are more de-shielded compared to the alkene protons, and that's why the carbonyl protons appear at higher delta value than the alkene protons. Okay, so you can see this proton is very close to the paramagnetic zone or de-shielding zone, which is parallel to the B0. Okay, so in this case at the center if it is there, it will be a diamagnetic. Okay, but in case of carbonyl protons, they are in the de-shielded zone, and even alkene protons are in the de-shielded zone. So this is another figure which explains the anisotropic effect of hydrogen atoms connected to a carbon-carbon double bond or alkene. So this is what exactly we are predicting, why the protons of alkenes are appearing at a de-shielded zone. So you can see the carbon-carbon double bond, this is actually influencing or opposing the applied magnetic field, which is a shielded zone. But in the periphery you can see the arrow is pointing towards upward, which is a parallel or aligned to the applied magnetic field on the periphery, and that's why these protons are in the de-shielded zone. Okay, the third kind of example in this anisotropic effect is a aromatic ring system. Now we know in case of aromatic ring system, which follows the rule of aromaticity, Huckel rule, in this case the delocalization of pi electrons are there. So in the ring structure, let's say in a benzene ring, there is a continuous delocalization or circulation of pi electrons for making it stable. So this particular delocalization of pi electrons will have something called as a ring current. Okay, and this ring current when we take this type of molecule under the influence of applied magnetic field, they will be aligned in this particular way. And the induced magnetic field which is generated around this, at the center towards the ring current, it is acting diamagnetically. Okay, and anything which is on the periphery, so these kind of protons which are attached to this kind of aromatic ring system, which are called as aromatic protons. So these aromatic protons are in the paramagnetic zone, or they are in a deshielded zone. So that's why aromatic protons usually comes in the region of 6 to 9 or 6 to 8.5 delta value. Okay, we can have some examples of this anisotropic effect. Take an example of toluene. Now in case of toluene, the CH3 protons are appearing at 2.34. So they are quite shielded. Okay, so though they are connected to a aromatic ring, but they are not aromatic protons. They are the protons of this methyl, and methyl protons usually appear at a delta value in a shielded zone towards the 0. We can consider this example where the CH3 protons are inside the ring. Okay, these are inside the ring. So this is a fused type of ring structure, and if you remember the previous slide where we have shown the ring current, so these CH3 protons are actually appearing in the diamagnetic zone because they are positioned in such a way that they are in the center of the ring, where the induced magnetic field of ring is exactly diamagnetic to a B0, and that's why these CH3 protons are highly shielded protons, and that's why they appear at a negative value. Okay, they appear at a negative value, that is minus 4.2. In case of aniline, which is a very classical example to understand the anisotropic effect, here you can see the 6 protons which are inside this particular ring structure. They are in a ring current zone, they are in a diamagnetic zone, and that's why these protons are appearing at minus 1.8 delta value, whereas the peripheral protons of this aniline, okay, they are in a periphery, so they are in a paramagnetic zone, and that's why they are appearing at 8.9, which is very close to 9. Okay, so that is the effect of anisotropy in this molecule. Similarly, when you have the structures like these one, in case of this is a chair conformation. Okay, so you can see here these protons which are connected to this particular ring structure. So this proton, I can say these are the equatorial protons, and if something is there in the axis, they are called as axial protons. Okay, so this effect is not much, it is approximately 0.5 ppm. So those protons connected to this particular ring structure which are in a equatorial position, so this proton as well as this proton, they are in an equatorial position, so that's why in equatorial position they appear in a deshielded zone. Okay, so because of the deshielded zone, they appear at a higher delta value. If the proton is in the axis, along the axis, right, so they are called as an axial proton, so they will be in a diamagnetic zone, so they will be bit shielded. Okay, so axial proton and equatorial proton, there is a difference of 0.5 ppm. Then we have the protons in this particular kind of aliphatic system, CH3, so they are appearing at shielded zone, that is near to 1.95. Okay, similarly we can account the effect in this case. If it is a kind of tertiary type of attachment where this hydrogen atom will be near to delta value 2. If it is a secondary, it will be in between 1 and 2. If it is a primary where we have 3 protons, okay, so obviously because of the 3 proton, it will have a very good electron cloud and it will be more shielded and it will be going towards the 0. Okay, and in case of strained molecule, this kind of strained ring, so these 2 protons will be near to 0. Okay, Now another example of anisotropic effect, especially with the alkyne group or acetylenic protons. So you can see this carbon-carbon triple bond is arranged in this particular fashion under the influence of B0. Okay, so this is exactly diamagnetic, and the protons attached to this carbon-carbon triple bond, okay, they are exactly opposing to the applied magnetic field B0, and that's why they are protecting in a very strong way from the B0. That's why they are in a diamagnetic zone. They are shielded protons, and because of the shielded protons they will appear towards the shielding zone or towards the 0. Okay, so these are the various factors which are affecting the chemical shift, and these are very important which need to be considered whenever you try to understand the NMR spectra. Thank you.